Next, let's move on to the 11th property, which is integration in time domain. Okay, so what does it say? It says let x of t has x of j omega as the Fourier transform. Then integral of this signal x of t, let us call that as x1 of t, which is equal to integral minus infinity to t. You remember that? How did we define integral of a signal? That is integral minus infinity to t x of tau d tau. So we have seen this extensively in second chapter and first chapters, correct? Yes. So this is given by pi times x of j0 delta of omega plus x of j omega by j omega. So Fourier transform of the integral of a signal is given by this. So let us prove this proof. Okay, so if you remember, we have seen that integral operation is linear and time invariant, and hence we can write this integral operation as convolution operation. Okay, let us write down that. So integral minus infinity to t x of tau d tau is same as what? If you remember, integral operation can be written as what? That particular signal convolved with u of t. Okay, now because convolution operation is there in time domain, that corresponds to what in frequency domain? Let us do that. So once I put an arrow, we are going into frequency domain. So what will happen? X of t will have x of j omega as the Fourier transform, and convolution will become multiplication, and hence x of t will have x of j omega, and u of t will have, you remember, pi delta of omega plus 1 by j omega as the Fourier transform. Okay, so this simplifies to what? This would be equal to, let us send x of j omega inside, you will get pi x of j omega delta of omega plus x of j omega divided by j omega. So this should be equal to how much? Any function multiplied with Dirac delta, what will happen? You should replace omega with 0. So you will get pi times x of j0 multiplied with delta of omega, and this term we will leave as it is, x of j omega divided by j omega. So that completes the proof of integration in time domain property. What does it say? Integral of a signal will have pi times x of j0 delta of omega plus x of j omega by j omega as the Fourier transform. Okay, right. So we will take a small example to how we can use this property. Okay, evaluate. Okay, question is evaluate the integral of a signal. Evaluate the integral of the signal x of t equal to e power minus at u of t. Okay, so we have to, question is we have to evaluate the integral of the signal. Let us call this to be x of t equal to e power minus at u of t. Okay, that is the question. Okay, so but how is the integral defined here? That is defined as x1 of t equal to integral minus infinity to t x of tau d tau, which is equal to integral minus infinity to t e power minus a tau u of tau d tau. So you can do directly in time domain, but let us do that in frequency domain. So we want integral of this signal. So but we know that the integral of a signal is equal to how much? The signal convolved with u of t. So this integral is same as, okay, so this integral is same as e power minus at u of t, and this fellow is convolved with u of t. So what will happen if you go into frequency domain? We get x1 of j omega is equal to how much here? E power minus at u of t will have 1 by a plus j omega, and this fellow is multiplied with Fourier transform of u of t. Why? Convolution in time domain will become multiplication in frequency domain. You will get pi delta of omega plus 1 by j omega. So let us substitute this. So this should be equal to pi times, what do you get? 1 by a plus j omega multiplied with delta of omega plus the second term would be 1 by j omega times a plus j omega. Okay, this is again looking like what? The function multiplied with delta of omega. So what should we do? We should replace omega with 0. So this will give you pi by a delta of omega plus, let us do partial fraction expansion. So what is the first step? You have to replace j omega with 0. So you will get 1 by a divided by j omega. So then you have to replace j omega with minus a. So you will get minus 1 by a divided by a plus j omega. Okay, right. So that would be the corresponding Fourier transform of which signal? Fourier transform of integral of the given signal, which is e power minus at u of t convolved with u of t. Now taking the inverse Fourier transform, what will happen? Or we'll write down in a nice way. This would be equal to 1 by a times pi delta of omega plus 1 by j omega minus 1 by a divided by a plus j omega. Okay, now let us take inverse Fourier transform. Okay, so taking inverse CTFT, what do we get? We get x1 of t. So this is completely x1 of j omega. So what will happen? We get x1 of t is equal to how much here? X1 of t would be equal to 1 by a. So which signal will have pi delta of omega plus 1 by j omega? We know that u of t will have that as the Fourier transform. Again minus 1 by a, and which signal will have 1 by a plus j omega as a Fourier transform? E power minus a t u of t. So this would be equal to, we'll write down in a nice way, 1 by a times 1 minus e power minus a t u of t. So we can write this two terms combinedly in this form, 1 by 8 times 1 minus e power minus a t u of t. So finally what did we get? We got integral minus infinity to t e power minus a tau d tau to be equal to how much? 1 by a times 1 minus e power minus a t u of t. Okay, so if you recollect, when we talked about convolution integral in second chapter, we convolved e power minus a t u of t with u of t and we got the same answer. Okay, so in that way, your wish. If you want to do this in time domain, you can do, and if you want to take the help of Fourier transform also, you can do. But I think personally, for this problem, Fourier transform is little bit laborious because we have to multiply and then take partial fraction expansion. But if you do convolution directly in time domain, it would be easy. Okay.